So this is an example where we will clearly need to use tangent normal coordinate system, because if you read the problem where there is a truck that is taking exit ramp with a speed v0, so its initial speed is given to you, which is v0. The ramp is a circular arc with radius rho equal to 150 feet. It's a constant radius term. Determine the constant rate of change of the truck speed that will allow the truck to stop at B. So remember our method. The method says that you have to pick your coordinate system. And in this case, it seems like because you're given the radius of curvature, the tangent normal system would be a good choice, right? Okay, so if you're using tangent normal system, then we have to write the velocity and acceleration in the tangent normal system. But before we do that, let's write down what is given to us, right? We should always start with that. So what is given to us is initial speed v0. The ramp is a circular arc, so we also know the radius of curvature. Determine the constant rate of change of the truck speed. Now this is very, very important. Constant rate of change of truck speed. So it's telling you that the truck speed is changing at constant rate, right? So what is the change of the truck speed? That's nothing but v dot. And the word constant over here is telling you that actually this is constant, right? So v dot is actually constant. So we will write v dot as a0, because this is a constant quantity and this is a some constant quantity, but we don't know what that number is. So is it 5 meters per second squared, 20 meters per second squared, or something like that? We don't know that, but we do know this actually a constant, which means that essentially v double dot is 0. Okay, all right. So we want to know what this a0 really is. Okay, so it's entering the ramp with the speed v0. That's its initial speed. Clearly this speed is going to pick up because there is a constant acceleration while it moves over the circular arc, right? Okay, so let's start by writing the expressions for velocity and acceleration in tangent normal system. So v is v et hat, and acceleration is given as v dot et hat plus v squared over rho en hat, right? So acceleration has component along tangential direction as well as normal direction. So if it is at point A, this is the tangential direction, this is the normal direction, right? If it is somewhere here, that's the tangential direction, and this is the normal direction. Okay, so what do we know about the velocity? Well, we only know the initial velocity, right? But if we knew how the velocity was changing, then maybe we could determine its velocity at all instant, but that is not something the question is asking for. Over here, we don't know what v dot is, but we do know it's actually a constant quantity. Okay, we do know what rho is, and we don't know how the v is changing, right? So let's start with v dot. So a0 is v dot, which is nothing but dv over dt. Okay, now in this particular problem, what do we know about the time that the truck takes to go from A to, let's say, B, or any other point on the track? We don't know what that time is, but we do know the distance it actually travels, right? So if it goes from A to B, going from A to B, the distance travel is basically nothing but, this is a quarter circular arc, so that would be 2 pi rho over 4, right? So that would be pi rho over 2. So we do know what is the distance traveled by this, right? In fact, we could tell you exactly how much distance it travels if we knew, what was the angle it was making from horizontal, right? Okay, so what we would do is we will do a little change of variable here, because we don't have the time information, but we do have the distance travel information. So we will write this as dv over ds times ds over dt, and ds over dt we know is v, so we will write this as v dv over ds. That's your acceleration. Okay, all right, so that's good. What we want to do now is we want to integrate this, right? So we will write v dv equal to a0 ds. We know initial velocity is v0. Finally, it comes to stop. So actually, I should add that v final is 0. So this comes to 0. And this will change from 0 to the distance pi rho over 2. So we are basically putting our limits for this integral from going from a to b. So what do we get? We get 0 minus v0 squared over 2 equal to a0 times pi rho over 2. So that gives us a0 as minus pi rho v0 squared. That's the acceleration, which is what the question was asking for, right? So the problem is solved essentially once we know the constant acceleration. But let's see if we can do something more than this, right? This is what the problem is asking for. Now we know the acceleration. If I ask you, tell me what is the velocity of this at an angle when this truck is at an angle theta from horizontal. Okay, I wanted to know that. Could you solve for that? You could. Now you know the acceleration. Acceleration is given as v dv over ds from this. You integrate it once more, but now your limits would not be pi over 2, but would be whatever distance the truck travels going from here to here, which would be, if you know this angle theta, would be basically nothing but rho times theta. So if theta is pi by 2, then you'll get to point B, but if theta is not pi by 2, you'll be somewhere in between. Okay, let's look at this problem where we will employ a different coordinate system. In fact, in this particular case, we will end up employing two coordinate systems. So in this example, we have a robot, okay, and that there's an end effector A. So think of end effector as your hand that can grab something. And the end effector A on the robotic arm needs to move the gear B along the vertical line shown in a specified fashion. So we have this gear B over here that needs to be brought down in a vertical line. And to bring it down, of course, you have the linear actuators over here. Essentially, they will extend in and out. And in this case, if it's coming down, you can see that the actuators have to extend, have to retract so that they can bring the gear B down. Arm OA can vary its length by telescoping via internal actuators. A motor at O allows the arm to pivot in the vertical plane, so it can rotate like this. When theta is 50 degree, B is moving downward with the speed V0 equal to 8 feet per second. So we know the speed at certain instant, and a downward acceleration with magnitude of 0.5 feet per second squared. At this instant, determine the required length of the arm, the rate at which the arm is extending, and its rotation rate. In addition, determine the second time derivative of both the arm's length and the angle theta. So there's a lot of information here. So let's start by writing down what is given to us. Okay, so given is at theta equal to 50 degree, V0 is 8 feet per second, and that's downward. So let me just show it graphically. And then acceleration is 0.5 feet per second squared, also in the downward direction. At this instant, we have to find the required length of the arm. So find, because we have quite a few things we have to find, so let's write that. Required length of the arm. So what the R would be, so let's say R is the distance OA. The rate at which the arm is extending, so that's R dot. Rotation rate, that's theta dot. And the second time derivative, so we are also looking for R double dot and theta double dot, right? So now if you look at the kinds of things that are given to you and the kinds of things that are asked for, the choice of coordinate system becomes obvious, right? And that's how in step number 1 in the method, choose the coordinate system. So we'll go with R theta coordinate system, and we will see if we need to bring in anything else, right, apart from the R theta coordinate system. Okay, so I'm going to draw this separately once more. So this is O, this is point B, that's the vertical line, and we will always have this right angle triangle, right? This angle is theta over here, and distance from, so this horizontal distance is given as 4 feet. I'm just going to call it B, okay, because B is constant. So B is constant. So B is constant 4 feet, okay, and B is coming down, right? So the velocity of B is downward, that's V0, and that's also the direction for acceleration A0. And OB is R, right? So this right angle triangle will always be maintained. Sometimes in problems like these, if you're given R and theta explicitly as a function of time, you will be in luck, okay? That wouldn't happen very often. Most of the time, an R and theta would be related to each other. So as theta is changing, R is changing as a result of that. So R and theta are not changing independent of each other, right? There is a relationship between the two. What is that relationship? We can write that cosine theta is equal to B over R. And this would be always maintained. B is constant, right? So we can write R equal to B sec theta. And that's the relationship that we have between R and theta. So if theta is known, which it is known in this case, so theta is known as 50 degree. From this, we know the B, so we can compute the R. So this part is actually easy to find. That doesn't even require any dynamics. This is basic trigonometry using which you can find what the R is. Okay, to get R dot, theta dot, R double dot, and theta double dot, we would have to do more than that. Okay, so what we can do is we can differentiate this once. So what do we get? We get B sec theta, tan theta, theta dot. Okay, so if we know theta dot from this, let's call it 1, we can get the R dot, right? I can differentiate it even once more. So I can differentiate once more. So we get sec theta, I will write this first, sec theta, and then theta double dot, plus b sec theta derivative of tan theta theta dot. But we don't know what theta dot is, so we cannot determine r dot. We could differentiate it once more and write r double dot as a function of theta dot and theta double dot, but even that won't take us anywhere unless we knew what theta dot was or what theta double dot was. Okay, so the only pieces of information that we have not used so far are these two, as to what V0 and A0 are given over here. Okay, so I'm going to show my coordinate system over here. My coordinate system is, this is the radial direction ER hat, and that's the theta direction, right? Why? Because theta is increasing in the counterclockwise direction. Okay, but we do know what the velocity is. So velocity is given to us completely. So all we have to do is write this velocity in terms of ER hat and E theta hat, and we'll be able to solve the problem. So let's do a little bit of geometry. This angle is theta. Okay, so this would be theta, and that means this would be theta, right? Okay, so what is velocity? Velocity is given as velocity in the radial direction ER hat plus velocity in theta direction E theta hat, and this is nothing but r dot ER hat plus r theta dot E theta hat, right? Okay, so what angle V is making with any of these vectors over here? This angle is theta as well, right? So V is actually uh, V is actually nothing but V0 cosine theta, and that's along minus E theta hat direction, right? And then we have uh, along the other direction, ER hat direction, that will be V0 sine theta ER hat. That is the resolution of velocity in r theta coordinate system, right? Because velocity is shown to be downward direction, all we are doing is resolving it along r and theta direction. Okay, so now it's easy to solve. We know that this is the velocity in r theta system, and that's the velocity that has been given to us. So let's just compare them. So what do we get? R dot is equal to minus v0 sine theta, and r theta dot is equal to minus v0 cosine theta. V0 is given to us, sine theta is given to us, so that gives us r dot. R is known, V0 is known, cosine theta is known, so that gives us theta dot, right? So we got from these two r dot and theta dot right away. Okay, of course we could have also taken r dot or theta dot from here and substituted in one and gotten the answer for the other thing. Okay, what about acceleration? Acceleration is similar. So acceleration in r theta system is ar er hat plus a theta e theta hat, which is r double dot okay, and acceleration is given to us, which is in the downward direction, so it would be minus a0 cosine theta e theta hat minus a0 sine theta er hat. So all we have to do is compare them. So compare, let's say this is 3 and 4, compare 3 and 4, what do we get? We get minus a0 sine theta equal to r double dot minus r theta dot square. So these two terms, this and this term, have to be same. So from here, a0 is known, sine theta is known, r is known, theta dot we just determined from the previous step. That gives us r double dot. Now let's compare this with this. So what do we get? We get minus a0 cosine theta equal to 2r dot theta dot plus r theta double dot. A0 is known, theta is known, r dot is known, theta dot is known, r is known. So that gives us theta double dot. So solving all of these gives us r dot, theta dot, r double dot, theta double dot.